We rolling? Okay. Good day again and welcome back. We are just finished with section 4.6 talking about polynomials today. Section 4.7, the last one in chapter 4, we're going to talk about rational functions today. Probably wondering, what is a rational function? Is it a function that thinks well? We'll talk about that today. That's the end of chapter 4. Chapter 5, we start talking about exponentials. So let's start today, chapter 4, section 7. Let's take a look at some rational functions. Again, my name is Jeremy Beckman. I teach at Natchez Valley High School, and this is part of CW's Cornerstone. What are we going to learn today? First off, we're going to be able to say what is a rational function. Second off, be able to determine the domain, the horizontal and vertical asymptotes of a rational function. If you don't remember what those are, we will review those real quick. And for some classes, we're going to review the translation of a rational function just based off of the most generic rational function we can find. So, as you can probably notice, some themes going on again as we've been talking about in this chapter. Domain, we're going to talk about range and how that has to do with asymptotes. So, first off, what is a rational function? A rational function, any function in the form y of x, y equals f of x over g of x, where f of x and g of x are both polynomials. And how I explain it to my students, it's a polynomial divided by a polynomial. In other words, if you just looked at the top, it would be a polynomial. If you just looked at the bottom, independent of the top, it would be a polynomial. Now, this is going to have some well-behaved parts for us, some things that are going to be able to help us get through and find the things we need to in this section. So first off, the base rational function, like for quadratics, the base function is y equals x squared. For a rational expression, it's y equals 1 over x. Now we're going to look at what 1 over x looks like, what are some features of it, what happens as x goes to infinity, what's its domain, what's its range. Give you a second to copy down. In fact, I'm going to flip back to the previous slide just so you have a second more to look at that. So let's look at this. Bring up a graph here. And in fact, let's graph our function. Let's take a look at what 1 divided by x. Now, before we even look at it, what's going to be the issue? What's going to happen with this function as we hit graph? Where is there going to be a problem? Yep, if you remember back even to grade school, elementary math, when you divide by 0, we run into problems. When you have a rational expression, when you have a rational function, anytime you divide by 0 or the denominator could equal 0, we're going to run into issues. So let's see what that looks like on the graph. Here's our function. Notice that it really looks like two parabolas, or two disconnected parts of a parabolic function. Let's take a look at some of the features. First off, when we looked at our original function, 1 over x, if we plug in 0, what's our output? That's 1 over 0. That's undefined. No, in other words, when you plug in 0, there's no output. It's not a member. There's no member of the range that maps up to it. So 0 is not part of our domain. We can tell that by seeing it as we go towards 0 from the left, we're approaching negative infinity. As we go towards 0 from the right, we're approaching positive infinity. In other words, those values that it's approaching from either side aren't equal to each other. As you start calculus, as you start 172, we'll talk about for a point to be existent, or for the function to be connected at that point, the left-hand limit, the right-hand limit have to be equal to each other. For this point, we notice as it goes to 0 from the left, as it goes to 0 from the right, going to two totally different points, or two totally different values of infinity. Also notice what happens as it goes towards infinity. In other words, as we keep going on and on and on and on and on, we're getting closer and closer and closer to an output of 0. So think of as we go towards infinity, as we go towards very gigantic values, 10 million, 20 million, 30 million, we're getting closer and closer to 0. Question to you guys though, will we ever actually hit 0? Answer no. No, we will get closer and closer and closer. In fact, if you told me how close you wanted to get to 0, I can tell you how far out you'd have to go to get there. However, we will never actually hit 0. Fortunately, sometimes your calculator lies to you. Like if you put 1 over 20 million into your calculator, some calculators will actually put out 0 for an answer, which is not correct. Let's look to negative infinity. As we go to negative infinity, we get closer and closer and closer and closer and closer to 0, but again, we never hit it. So thinking of, okay, what's the value of the range that we'd never hit? Well, as you can see, we'll hit everything below 0 down to infinity. We'll hit everything above 0 and down to infinity, but we never actually hit 0. We get closer and closer and closer, we never actually hit that. So let's have some definitions real quick, just in case you forgot what they are. An asymptote of a curve is a line such that the distance between the curve and the line approaches zero as they tend towards infinity. In other words, it will get closer and closer and closer to that value, but never actually hit it. As we'll explore in this section, they can be vertical or they can be horizontal. Typically on a graph, they'll be represented by a dotted line. Let's go back to our graph real quick. So what values or what points vertically will we get close to but never actually hit? In fact, let's put in a line at 0. If we plug in 0, and let's make this a dashed line. So for this particular graph, the only vertical asymptote we have is at x equals 0. In other words, we get closer and closer and closer to it, but we never actually hit it, typically denoted by a dotted line. Let's also look at a horizontal asymptote. What number do we approach but never actually hit? That's at y equals 0. So let's put in a dotted line there. So with our asymptotes drawn in, here's our function. We can see several things are going on again as we go towards infinity. We go towards 0 in the y values. As you get closer to 0, you're going towards infinity. As you're going closer to 0 in the x values, you're going closer to infinity on the y's. So let's take a look at an example. Again, the things we've been pushing for, the things we've been continually hitting in this book. We're going to talk about what happens when it's translated. We're going to talk about what happens when we stretch it, compress it. But first off, let's just record some basic values. Let's go to the DocCam, take some notes on the properties of the properties of rational functions. There we go. Okay, some notes. Its domain is all real values except 0. We'll write that in interval notation here that goes from negative infinity to 0 and 0 to positive infinity. Its range, and kind of odd with this, its range, what value does it never hit again? Never hits 0. So again, we could go from negative infinity to 0. And we could go from 0 to infinity. So kind of weird. The domain and the range are the same. However, there's still an asymptote on both the horizontal and the vertical. Again, this one has a vertical asymptote. Again, verticals up and down. So question to you, it's at 0. The vertical asymptote, do I put x equals or y equals? Again, it's vertical, it's up and down. Yep, x equals. The horizontal. Now, why is that confusing? Why is a horizontal asymptote a y value? Why is a vertical asymptote an x value? When you usually think about the horizontal axis, you're thinking about, okay, where's our x value that we put in there? Well, what's the line at the horizontal asymptote? It's y equals 0. So that is a horizontal line for y. All right, let's take a look. Let's go back. Let's take a look at a translation. Let's get that value in. Let's switch back to the PowerPoint here. And let's take a look at our first example. Find the horizontal and vertical asymptotes using only translation. So in other words, now we're not going to discover the algebraic way to find this, but just using translations. How could we write the vertical and the horizontal asymptotes? So let's take a look, see how we solve this one out. Again, here's our original function. Now, here's this question I ask my students. This is a new one. This is unfamiliar territory. How could I write a quadratic that had the same translation? Now, why? Because this might help you understand what we have to do with this one, but how could we write a quadratic that had the exact same translation as this rational function that we have over here? So the base function, again, for a quadratic, start with y equals x squared. Now I call my students on to what's the action of this function? You're squaring x. So when you move left or right, you have to do that in parentheses or before you square it. So this one, what's the action of this function? Well, it's 1 over the x value, or it's a reciprocal of the x value, 1 over that. So as we take a look, before we do that, we have a plus 3. Because it's before the action, remember it's the opposite, so plus 3 ends up moving 3 to the left. So how could we write a quadratic with that? Well, we need to move 3 to the left before we square it. Now, after the action of this function, we have to move 1 down, or 1 down, or negative 1 values up or down. How can we do that with a quadratic? We'd have to, outside of the parentheses, minus 1. So with this one, below our division bar, that's where the action of this function is. So anything you do before that moves it left or right. Anything you do after that moves it up or down. So what does this one move? It moves it 3 to the left and 1 down. So as we looked at in our notes, we started with a vertical asymptote at x equals 0. A vertical asymptote at x equals 0. We translated everything 3 to the left. So our vertical asymptote in this one will be at x equals negative 3. Moved everything 3 to the left, so now our vertical asymptote would be at x equals negative 3. A horizontal we started at y equals 0. We moved everything 1 down, so our horizontal asymptote, will it be a positive 1 or negative 1? And yes, a negative 1. Cornerstone teachers, if you'd like to take a second, talk about how that translation worked. I think seeing it as a quadratic brings you back to something that's familiar, something you've seen before, something you know how to deal with. That'll help you deal with the newness of this function. For those of you here on campus, let's take a look at our sketch of this and just verify. Thank you for switching that. Let's verify our function here, and let's in fact even remove, let's just go to a new graph here. Let's go find our coordinate system, and we want to plot a function. These are a little bit more complicated to plug in. We have to go 1 divided by parentheses x plus 3, and then outside of that minus 1. And let's look where, on horizontally, where does it approach but never actually hit? Okay, that's at negative 1. Good, let's draw on that line. Oops. Gotta select line first. And where vertically we approach at negative 3, we never actually hit. Let's draw one in there. There we go. So what we saw by translation, now verified by taking a look at the graph. All right, questions on that? Okay, hearing none, let's move on to the next topic. Horizontal asymptotes, how do we find them algebraically? We'll talk about vertical in just a second. That's what vertical is, what member of the domain does not give us an output, or what value we approach. Horizontal asymptotes. What happens is x goes to infinity. Now there are a variety of ways to teach this. I'm going to look at the algebraic way. We've looked at the graphic way. Your teacher might also add in another way to take a look at this. But let's take a look as x goes to infinity. Where is this function going towards, or what's happening to this function?